Howdy everybody, my name is Bailey Faulk, and I will be touching on some of the theory for Chapter 7, which is on synchronous machines. Okay, so for the agenda today, we'll be going over three topics. We'll be going over a quick introduction of synchronous machines. Then we'll be understanding more of the magnetic stuff, so looking at one phase, two phase, and three phase, ramping up from there. We'll be looking at co-energy, flux linkages, torque from electric origin, etc. And then lastly, we'll be touching on how to solve some of these problems. So looking at three-phase, per phase, equivalent circuits, and things like that. So diving into the introduction. So what exactly is a synchronous machine? So a synchronous machine can be either a generator. So you put in some sort of mechanical power, and then you output some electrical power. Okay, right? This is our synchronous machine. A motor, you could input some electrical power into our machine, right? And then it'll output some mechanical power, right? So like it's an engine or a motor for our car, right? It could also be a power factor correcting device, and we'll touch on that a little later. How do they work? How does a synchronous machine work? Well, it's made up of two components, the rotor and the stator. So the rotor here is excited by a DC field winding, okay? Right, DC field winding. And then the stator, which is what I'm circling here, that's excited by an AC winding, okay? And so what these two do is the AC winding creates a magnetic field, and the DC winding will rotate in that magnetic field. So what are some examples of this? Well, there's car alternator. I'm sure you've heard of that. Maybe an AC generator for a wind turbine, right? So it does this. It takes in the mechanical power of the turbine spinning, right? And then it outputs some electrical power for the grid, right? Okay, so next, let's touch on a ramp up, right? Let's touch on the magnetic details of these synchronous machines. So starting with one phase, okay, so let's take a look at this diagram here. So with the one phase, we're inputting our AC phase here, and then we're hooking up our DC winding to the rotor here, okay? So from this, we get two flux linkage equations for the stator and then for the rotor. This is what we'll see here. One thing I want to note with all these, with what I'm going into with the magnetic side, is I won't be touching too much on the details for the derivation. I'll be going over overall details and things that I find important. And one of those things that I really find important is that steady state, the steady state power. I'll be touching on that for all three, for both one, two, and three phase synchronous machines. So looking at one phase at the steady state power for one phase, it's going to be this equation here. Okay, so omega m is going to be the combination of the stator frequency and the rotor frequency, the frequency with which they're rotating, and then this is and this ir. Those are the currents that are inputted into the stator and the rotor. So right here is is for the stator, IR here for the rotor. So one thing we want to know with this is you can't tell just from this equation, but what's going to happen is there's going to be this pulsating torque, this pulsating torque, and that's because we have only one coil on the stator. Okay, and so what we're going to see is that a two-phase machine will allow us to fix this because it creates a rotating torque, a rotating magnetic field, where the magnetic field will continue to rotate. It won't be stationary like this one is here, where there's the axis for the magnetic field, and it's gonna be stagnant. No. For the two-phase, we'll have a rotating magnetic field, which will allow us to prevent that pulsating torque, right? That's one thing I wanted to mention here. But this is where we get the steady state power for a one phase synchronous machine. Moving on to two-phase synchronous machine. So these are those flux linkages here. Oh, before I get into that real quick, this is what that two-phase looks like. We have two coils here, and these two coils are rotating around this rotor coil, quote unquote, rotating around the rotor coil. The rotor is actually the one that's rotating, and these two coils are these two stator coils are remaining stationary. But getting back to this, this is the co-energy equation for our two-phase, and then this is the torque from electric origin. Okay. Anyways, let's keep moving forward. Let's look at the average power and constant power, right? So let's take a look at how this two-phase machine works in steady state. So let's assume that we have these currents, these current equations here, right? So as you can see, IAS, IBR, IBS, IAR. Okay, so these equations here are over in this diagram, right? So after a lengthy derivation, we come up with this equation here. Okay, we get that PM, the mechanical power, is equal to the origin, the torque from electric origin times this frequency, which is equal to this equation, right? Where we see it's the mutual inductance times the phasor, or no, I'm sorry, the stator current and the rotor current times this sinusoidal function here, right? That's dependent on dependent on time, right? So what this gives us is it gives us the average time varying with respect to, it gives us the average power with respect to time. If we're in steady state, then we're not really given a time. The time is all time. It's from negative infinity, right, to plus infinity, right? So that doesn't really help us with constant power. Well, that is one of the conditions that we have to have in order to solve for this constant power, right? We have to make this term right here be zero. We have to get rid of this t term. Okay. So we have to make this total frequency equal to the stator frequency and the minus the rotor frequency. We have to eliminate these two, right? And so if we have two windings that are 90 degrees physically apart and phase currents that are 90 degrees apart, like we do for this two-phase synchronous machine, then we're able to have a single frequency condition and no pulsating torques, right? Like we did for that one phase. And so we're able to get a constant power that's equal to this equation right here. Okay, moving forward, let's also look at what a rotating magnetic field looks like, okay? So with these currents, in each of these windings, they're producing a flux density, okay? They're producing a flux density. And so this flux density is going to vary with respect to time, right? We have these time equations here. So if we have a flux density that's varying with respect to time, then we can expect for also our magnetic field to vary with respect to time, right? So as our flux densities are varying, then our magnetic field is also varying with respect to time, right? Like we see here. And our magnetic field is actually rotating at a speed of omega s, or the frequency that our stator is moving, right? So this rotor magnetic field is created by rotor currents that are excited with the rotor frequency. And what's going to happen is the stator and rotor magnetic fields are going to align themselves, okay? And what's going to happen is that the power conversion occurs when these two fields are fixed relative to each other. And the rotor is going to be turning at a constant angular velocity of about 2 pi 60 radians per second, right? So that's the key, is that we need to have these magnetic fields align themselves in order for us to have that that rotating magnetic field. Okay. And then next, three-phase. So with three-phase, we have two types. We have the salient rotor, where the air gap varies, and we see that right here. We see the air gap is varying. It's not constant like it is in the round rotor, where that air gap is constant, right? So with the three-phase figure, as we know, the rotor carries that constant current IR because it's DC, and then the stator coils are spaced 120 degrees apart. So these stator coils right here, they're spaced at 120 degrees apart, and each coil creates a sinusoidal magnetomotive force around the edge. Okay. So real quick, for both the salient and the round rotor will have different flux linkage, co-energy, and electric origin torques. Like I said, I won't get into the derivations, but quickly, this is what the flux linkage is. One note is that the matrix is symmetric. The co-energy is here, and then the electric origin is here. One thing you'll note is that this LR term is missing. And that's because it's not a function of theta. The rotor inductance is not a function of theta. Okay, moving on. The round rotor flux linkages are as follows. So this is the flux linkage, the co-energy, and the electric origin torque. Once again, won't go in depth about these because we don't have the time. But I highly recommend that you double check or you look at these, make sure you understand them in the textbook. Okay, now let's take a look at the steady state power. This is what we're focused on, the steady state, right? The steady state. So let's take a look at the average power when we are given these currents, these balanced currents, right? When they're about 120 degrees phased from each other. So when we're given that, then what we're able to do is we're able to find the average electric origin torque, and we're able to get this equation here. And then from here, we do some more substitution, and we get this equation right here. What's important to note is, okay, where are our t terms, right? Where are our t terms? That's the most important thing when asking, how do we get the steady state? How do we get the steady state? We eliminate time dependence, right? We get a constant. So what we need to do is we need to get this condition to be met when omega m is equal to omega s, right? And when this happens, then we're able to get a constant. We're able to get this term right here for our electric origin torque. One thing to keep in mind, if you haven't already picked up on it, is that the average power is equal to the electric origin torque times omega m times this frequency, right? And so we're able to get is that average power is equal to this quantity here. Okay, lastly, let's go over to solving, right? Like what do these equivalent circuits look like, right? Let's take a quick deep dive into that, okay? So this is what an equivalent circuit looks like for a phase in maybe a generator or a motor or that power factor correcting device that a synchronous machine can perform as. So VA right here, let me get my annotator out. VA, this is going to correspond to these two terminals here, right? For our phase. EAR, right? So EAR is going to be the voltage phasor that is proportional to the field current or this rotor current right here. Okay. And then this is going to be some impedance, right? Some impedance that's faced in between the stator and the rotor, right? And then going from there, phase B and phase C. These will be phased in relation to where our reference angle is. And in this example, we chose that phase A or angle A was going to be the reference angle, and so we're going to base everything off of that, right? So IB equals IA angle negative 120, et cetera, et cetera. So it's very, very similar to what we learned back in chapter 2. So looking at the equivalent circuit for the motor, this is going to be the bread and butter. This is the key right here, is that the motor is transforming electrical power into mechanical power, and this is what that that equivalent circuit looks like, okay? Okay, so looking at some equations for this, one thing to keep in mind is this equation here, okay? So the total power is going to equal this -3 times EAR, the voltage at EAR, times VA times sine of the torque angle divided by our impedance, right? Right here. So real quick, just want to touch on this leading versus lagging power factor. It's going to be dependent on theta, right? Our power factor angle. So whenever theta is positive, then we're gonna have a leading. Whenever theta is negative, we're gonna have a lagging, okay? All right, let's clear this out. And let's move on to generator, right? Generator. So once again, this is critical to understanding how to solve a generator circuit, okay? So our leads are hooking up right here. This is our rotor dependent voltage source. And one thing to keep in mind is that the generator is taking mechanical energy and it's pumping out electrical energy, right? So this is going to be our power for the generator. That's just kind of one thing to keep in mind is that the signs are different. The signs are different. So keep that in mind when solving these. So I'm gonna sound like a broken record, but make sure that with your power factors, leading and lagging, you're keeping track of the signs of your angles. So when theta is positive, plus theta is negative, lagging, et cetera, et cetera. So moving forward from there, let's take a look at total and reactive power. So we took a look at real power. Let's take a quick look at total complex power, right? S. So S is going to be equal to 3 times the voltage phasor and times the conjugate of the current phasor. And how do we get reactive power? So we have S. Now we had P, or we had P at the last slide. How do we get Q, right? How do we get Q? So Q is just going to be equal to S minus P, right? The complex power minus the real power. So if we know if you know the complex and we know the real, then we can find Q. One thing I wanted to remind y'all of, I know I mentioned this earlier, but make sure you remember this formula. It'll sneak up on you on some of these problems, but the torque of electric origin is equal to the mechanical power divided by this frequency term here. Okay, and then lastly, let's take a look at power factor correction. So we talked about how it can be used as a generator, synchronous machines that is. We talked about how synchronous machines can be used as a motor, but now we're going to talk about how it can be used as a power factor correction device. So what we can do is we can vary the value of the field current or the rotor current. And by varying that value, we can make the phase current vary from lagging to leading or leading to a lagging power factor, or maybe even bring it to a unity power factor. And what we can do is we can make this an underexcited or overexcited synchronous motor. And by doing that, we're able to bring it to power factor unity, right? So as you can see here on this diagram, as we increase the field current, we can transition it from an inductive synchronous machine to a capacitive synchronous machine. Okay. All right, and then lastly, what I'm going to cover is rotation speed. Okay, so this is one thing you'll see in a lot of the problems is poles. So this is gonna be like a 6-pole, 60 hertz synchronous machine, etc., etc. Maybe this is like a 2-pole synchronous machine, etc., etc. Well, the number of poles, actually, let me take a step back. What exactly is a pole? Well, a pole is the magnetic pole of a machine, right? So let's take for example. So this synchronous machine has 2 poles, North Pole and South Pole. This synchronous machine has 4 poles, 2 south poles and 2 north poles, right? So what we're gonna see is that with 2 poles, it takes one mechanical revolution to get through one electrical revolution, right? So I go 360 degrees and mechanically, and I end up one revolution around all the poles, right? However, for 4 poles, it takes quote unquote two mechanical revolutions to get through all electrical poles, right? So I have to go through these 2 poles, right? And I go through these 2 poles here, right? So more generally, the equation is this. So the frequency of the electrical rotations is equal to the poles over 2 times the mechanical frequency. I find this diagram to be a little more helpful than my explanation. So as you can see, the theta for mechanical, it's not increasing or decreasing, but the number of times that we hit a pole, right, or that our H value hits its maximum, that will vary depending on the number of poles, right? So yeah, that's one thing to keep in mind. Why is this significant? Well, it depends on it's important with regards to speed, right? So as the number of our poles increases on a synchronous machine, then the mechanical frequency will decrease, but the electrical frequency will increase, right? So the relationship between the frequency and number of poles is going to be this formula. This is your bread and butter right here, where this synchronous mechanical speed is going to be equal to 60 times the mechanical radians per second over 2 pi. And then P is just the number of poles here. All right. So that about wraps up our equivalent circuits. Hopefully I was able to do a decent job with explaining all this to y'all. I was only able to do everything in a short amount of time, but I highly recommend that you take a look at all of this in the book. The book does an excellent job of explaining most of this and all of this. So I believe that Dr. Davis will post these slides, and you can use these as a sort of supplement while reading the book. This is a quick recap for what I covered in this last section. But yeah, if you have any questions, please feel free to reach out to me, Molly or Ian, with those questions. And I hope you have a great final season. Best of luck.
Here's an example problem for us to work out together. The problem states, a 3-phase 60 Hz, 550 volt Y-connected synchronous generator is delivering 250 kilowatts at rated voltage. The excitation voltage is 460 volts per phase, and the synchronous reactance is 1.2 ohms. Calculate the torque angle, delta, find the generator current, power factor, and reactive generation Q, and then, for the same terminal voltage and active power generation P, determine the excitation voltage to achieve a power factor of 0.8 lagging. What is the new value of the torque angle, delta, in this case? So I like to start these problems by listing out what I know what is given to me in the problem, right? So I'm going to read this question and I'm going to write down the things I know. So I know the excitation voltage is 460, or at least the magnitude is. And I know that the total power is 250 kilowatts. I know that the three-phase synchronous generator is 550 volts. So really, if we want to analyze this per phase, we're going to say that the phase will be A. It will be 550 divided by square root of 3. So we also know the synchronous reactance. It's 1.2 ohms. And then, of course, most important, synchronous generator. So that gives us the convention we want to use. Now, the first part is asking us for delta. So how do we solve for delta? The first thing I like to do is to draw the per phase equivalent circuit, which I did so here. And the reason that the excitation voltage is a dependent source is because its magnitude is proportional to the field current. So it depends on something. So we draw it as a dependent source. So then I'm going to continue filling in these values so that I know what to use. And okay, so first what I like to do is take the voltage as reference. So I say that VA, since we're using phase A, is 550 over square root of 3 with an angle of 0, since I decided to set it to 0. And then the excitation voltage is 460 with its angle being delta, which is what we're looking for. Oops, I did not mean to write that. And then we know still this is 1.2 ohms. And then now, what can we do? So we know also that the total power is 250 kilowatts. So on top of this, we know the formula, or we should know the formula, that the total power is equal to 3 times the magnitude of the per phase voltage, the excitation voltage, times the sine of the delta divided by the synchronous reactance. So now what we'll do is we'll plug in all the values we know. So we know that PT is 250 kilowatts. It's equal to 550 square root of 3. And then 460 times sine of delta divided by 1.2. And if you're wondering why I'm not using these angles, the ones right here, it's because in this formula we use the magnitudes. So that's what these little lines are for. That's a phasor. And then the rest are magnitudes. So if we solve this out for sine, or for delta, then delta should be about 43.2 degrees. And we would do so by basically multiplying and dividing out and getting it to be an inverse sine of a bunch of numbers. Or I guess it'd be one number at the end. So now that we found delta, let's find the generator current, the power factor, and the reactive generation Q. So let's fill this in again. I think I forgot the J here. It needs to be there. So we want to find the generator current, which is simply IA. And it's as simple as Ohm's law, because we just want to do IA is equal to the excitation voltage. Right, so this is just classic Ohm's law. So we're going to find the phasor of the generator current. So we have to use not the magnitudes, but the phasor values of the others. And we solve for delta, so we already know what this is. So we're going to do, this is 460 minus. You don't actually have to write the 0, but I like to just so that I know. And then this should give you a value for this generator current to be about this. So actually, we can solve for the power factor right here. The power factor is the cosine of the angle between VA and IA. So in this case, since we chose VA, or voltage of phase A, I guess, to be the reference and I chose it to be 0, the power factor is the cosine of the angle of the generator current. So we take this and we say 3.24, right? So this will give you a value of 0.998. And we have to state that this is lagging. And we know this because of this sign. So now we have the power factor. So we can move on to the last part of part B. So basically what it's asking for is the reactive generation Q. And actually, this power factor angle comes in handy for solving for the reactive generation. So if we move here, we can say that QT, which I'm going to call it QT, but you can call it Q. This is the reactive generation. And so how do we solve for that, right? Like new value. So if we keep in mind that the complex power of a synchronous generator is equal to 3 VA IA conjugate, and we also remember that this is PT plus JQT, then we can solve for QT. So really, we want to look at this one. We know from this then that QT over PT is equal to tangent of the power factor angle. So then we can solve for QT by shifting that around and multiplying it by the tangent of that power factor angle. And we should get that QT is about 14.1 kVAR. So now that we've found the last part of part B, we can move on to part C. Part C is asking, for the same terminal voltage and active power generation P, determine the excitation voltage to achieve a power factor of 0.8 lagging. What is the new value of the torque angle delta in this case? So we're told we want to keep the same terminal voltage and active power generation P. So we're also told that we have a PF, a power factor of 0.8, which we can find the power factor angle, or I guess I'll name this phi, by taking the inverse cosine, and we get that this is equal to 36.87. So that doesn't tell us much anyway, but it is useful because we will be using that angle as part of the phasor for the power the generator current, right? So this will be something, and this will be this, right? And it's lagging, so it's going to be that because of we're told that it's lagging. So we know that the active power is 3 VA IA times the power factor. So we can just plug in these values to get IA. So we're going to do, these are the magnitudes since we don't need to use the phasor since I found the angle, right? We found the angle. So if we just plug in the things we knew, this would be 250 kilowatts equal to 3. And then VA is 550 square root of 3. We don't know this, so I'm going to set this, or I guess we can just use IA again. And then we multiply this by 0.8. And that'll give us that IA is equal to 328.04. And we know the angle, so we can do this. And it's this. This is the generator current's phasor. And so why do we need this? Right? It's asking for the excitation voltage and it's asking for delta. So why do we need the generator current? Well, actually, the generator current has a relationship with the excitation voltage, right? So for this convention, VA is equal to negative J XS IA plus the excitation voltage, right? And we can rearrange this to get this relationship, which is full of known numbers, or I guess known values would be more correct to say. So this is exactly what we're looking for. And this will give us delta since the angle is delta. So if we move this way, we can say right? And this is this, right? You still don't have to put that 0. I just put it because I like having it. And then 3, 2, 8. Oops, I wrote a little too bit. J 1.2. And so if we solve this all out, right, this will be equal to this. We get that the excitation voltage is equal to this, right? And it did ask us for delta, right? What's delta? This angle. So delta will be so now we have finished the problem. We have effectively found the torque angle with the original problem. Then we found the generator current, the power factor, the reactive generation, and then we now had a new power factor of 0.8 lagging, and we found the new torque angle and the excitation voltage. What I would like to comment on is that these problems for this chapter, chapter 7, take a lot from, I believe it was chapter 2, right? The chapter that covered three-phase systems. These relationships are very similar, and using those concepts may help a lot with these problems. So keep that in mind when solving these problems. It's not that different from what we've looked at before.
Example 7.4 has a 1000 kVA, 3300 volt, 60 hertz, 4-pole, 3-phase Y-connected synchronous generator, and it has a synchronous reactance of 1 ohm. The generator is delivering power to a load at a power factor of 0.8 lagging and at a rated voltage and at rated current, and then it asks to find the speed, EAR or the excitation voltage, delta or the torque angle, and the torque of electric origin. So to start with the speed, the mechanical frequency is going to be equal to 2 times the synchronous or electrical frequency over the number of poles. So that will be 2 times 2 pi 60 radians per second over 4 poles. And that will be 60 pi radians per second. And then if we want to convert to RPM, 60 pi radians per second times 60 seconds in 1 minute times 2 pi radians in 1 revolution, and the mechanical frequency will be equal to 1800 RPM. The next thing it asks for is the excitation voltage, but after finding the speed, we can find the torque of electric origin very directly, so I'm going to do that next. The torque of electric origin is just simply equal to the power over the speed, but it gives us S 1000 kVA. So that's, if we recall our power triangle, here's P, here's S. So P is just going to be equal to S times the power factor. So 1000 kVA times 0.8 all over 60 pi. So TE, the torque of electric origin, is going to be equal to 4244 Newton meters. So the next thing we're going to find is going to be the excitation voltage. And to do that, we're going to use the following relationship. The excitation voltage is equal to VA plus JX sub S IA. VA, just like in three-phase power, is going to be equal to the total voltage, 3300 volts, divided by the square root of 3. And then we're going to say that this is the reference point for phasor notation, so it's just going to have an angle of 0. And then IV, again, just like in three-phase power from earlier in the semester, we can find the magnitude of it using this relationship. I is equal to S over V, the magnitudes. And then the magnitude of S is going to be the total 1000 kVA divided by 3. And then, as we just said, the magnitude of VA is going to be 3300 divided by the square root of 3. So IA has a magnitude of 174.95. And then to find the angle, we're going to use the power factor. Where the angle is the inverse of the power factor. So IA is going to be 174.95, angle 36.87 degrees. And because it's lagging, we know that this is going to be a negative angle. So EAR can now be found using what we just identified. So VA 3300 volts over square root of 3 plus J X of S, which was 1 ohm, times IA, which was 174.95, angle negative 36.87 degrees amps. So EAR, if you plug it into your calculator, should turn out to be 2015.1, angle 3.97 degrees. And then the last thing the question asks for is delta, or the torque angle, and that will actually just be this angle right here. So EAR torque angle is just going to be equal to 3.97 degrees, and that is 7.4. Example 7.10 has a three-phase, 60 Hz, 550 volt Y-connected synchronous generator delivering 250 kilowatts at rated voltage. The excitation voltage is 460 volts per phase, and the synchronous reactance is 1.2 ohms. The first thing it asks for is the torque angle, delta. And to find that, we can use the following equation. Power is equal to 3 times the excitation voltage times the per phase voltage times sine of the torque angle divided by the synchronous reactance. And then solving for the torque angle, we get inverse sine of power times synchronous reactance all over 3 excitation voltage and then per phase voltage. Plugging in, we get inverse sine of power is 250 kilowatts The synchronous reactance is 1.2 ohms. The excitation voltage, 460 volts. And then for the per phase voltage is going to be equal to 550 volts divided by square root of 3, just like how we would in three-phase power. And then if you plug that into your calculator, we should get 43.205 degrees. For the torque angle. Part B asks us to find the generator current, the power factor, and the reactive generation Q. To find the current, we can use the same equation from example 7.4. That is, the excitation voltage is equal to VA plus J XS I. Rearranging for I, we get EAR minus VA over JXS. EAR is going to be equal to the 460 volts given with an angle of the torque angle, our result from part A, and that was 43.21 degrees. VA is going to be equal to 550 divided by square root of 3. The 550 is what's given to us, and then we divide by square root of 3, just as we would from three-phase power earlier in the semester. And then J, 1.2 ohms. Plugging into our calculators, we should get that the current is equal to 262.85 angle negative 3.23 degrees. Our power factor is just going to be equal to the cosine of the angle we just got for our current. That is 0.9984. Because the sine of the angle in our current was negative, we know that this power factor is lagging. The last thing part B asks us to find is the reactive generation Q. To do this, we can use this equation. S is equal to 3 single phase voltage times the conjugate of the single phase current, or the per phase current voltage. Plugging in, we get 3, again, 550 divided by the square root of 3. Angle 0 as it's our reference. Then our current was 262.85. And then our angle is going to be a positive 3.23 because we took the conjugate. Plugging into our calculators, we should get that S is 250 plus J 14.095 kVA. And then Q is just going to be the imaginary component of S. So we get that the reactive generation should be 14.095 kVAR. So part C asks us to find the excitation voltage and the torque angle in a case where the active power generation and terminal voltage is the same as in part A and B, but we have a power factor of 0.8 lagging. So to do this, we can use the same equation from part B, except just work with the magnitudes first, where the magnitude of S is going to be equal to 3 times the magnitude of the per phase voltage times the magnitude of the per phase current. So solving for the current, we get magnitude of S over 3 magnitude of the voltage, and then S is going to be equal to the power, 250 kilowatts, divided by our power factor of 0.8, and then our voltage, VA, is going to be equal to 550 divided by the square root of 3. So the magnitude of our current is going to be equal to 328.04. And then our power factor, or our power factor is going to be 0.8 lagging. So cosine of 0.8 will get us the angle for our current. So the current will be 328.04, angle negative because it's lagging, 36.87 degrees. And again, the 36.87 came from cosine of 0.8. From here, we can plug in I and V to this expression again to get the excitation voltage. So VA, 550 volts, divided by the square root of 3, plus J, 1.2 ohms, and then our current, and that gets us our excitation voltage. And if you plug that into the calculator, you should get 637.02, angle 29.6 degrees. So that is our excitation voltage. And then our torque angle is just the angle of our excitation voltage, 29.6.